So in the last video, we derived our ds, this arrow that walks along our curve, and we got the link between ds and dx so that we can go our usual left to right and still walk along the curve. And we use that to find the arc length of some kind of cherry-picked examples that we had to do some serious algebra to get out from under that square root. For surface area, we're looking at rotating again, like we did before with volumes, taking some function and then rotating around an axis. And we want just the outside, right? The surface area of it this time. So just to draw a picture of what we're looking at, sort of. So we got some function. I don't know why I always draw like basically a cubic, but whatever. And we're rotating it. So let's rotate it around the x-axis here, something like this. So this would sort of bow out a little bit and then go in and then out, something like this. Okay, and we're just looking at the outside surface area. So what I'm doing is I'm taking a cross section. I should have maybe made that more dramatic. So I'm taking this cross section, and it's not a cylinder, but it's what's called a frustum of a right cone. Okay, maybe if I try to draw another one, I should have made that curve maybe a little more dramatic. You see this outside edge is traveling along with the curve. That looks like something we saw in the last section. Eh? But what I was saying was what we're actually adding up is what's called the frustum of a right circular cone. So it's a cone that's been chopped off, basically. And so we have this small R1, one radius, and then another R2 radius. It has a height, h, and then the length of that side there, we usually call L. L is the slant height. It's that distance on the side here. And we're seeing it here and here. Okay? Now the lateral surface area of a frustum is pi R1 plus R2 L. Again, where the L is that slant height. But, okay, what we're doing here is, we got to remember these are slices. So the height here in this orientation is just dx. It's infinitesimally small. In this orientation, if we were going up this way, then that height would be dy. So again, it's infinitely thin. It's infinitesimal. So these two radii, they're essentially the same circle. They have the same radius. R1 is equal to R2. So we get this 2 pi r, two r's from here, assuming that these are essentially the same, because they're so close together, L. Okay. Now, that L, like I've been saying here, is this length that walks along with the curve. Right? It's the slant height on the side of that frustum. That we already figured out. That's ds, that little slant height. So if I'm trying to find the surface area from A to B, then that's really all I'm doing. To get the arc length, we just integrated ds, the length of those little arrows as we go along. Here we're going to integrate 2 pi r ds, 2 pi r ds. So the 2 pi, that's constant, I can pull it out. Integral A to B ds, oops, r, 2 pi r ds. That's the surface area, 2 pi r ds from A to B. Surface area. Okay, but again, saying 2 pi r ds, okay, great, that's what we're doing. We're adding up all these lateral surface areas as we walk along dx, but this ds, so we need that link, right? So let's rewrite that in a manner that's usable for us. And we'll have our final version. So the surface area is 2 pi integral from A to B. R is a function of x. Let's stick dx. If we were doing it dy, it would be r as a function of y. So we have our radius. We can allow it to change. And then ds. Well, ds is the square root of 1 plus the derivative of f squared dx. That's it. 2 pi r ds. Okay. So again, we're in the same situation as with arc length. The setup isn't all that bad. Again, now, like when we were doing volume problems, we do have this additional challenge of figuring out what this r is. But otherwise, the main difficulty, again, is the fact that we have this composite under the square root. So we have to deal with that. But it's often very nice that this r of x function is outside, because then we'll be able to u sub. And we'll actually have the extra stuff outside that we need in order to do that. So even though this adds an additional layer of complexity or another thing to find, it actually ends up helping very often. Okay, so let's look at a basic one to start. Let's say we have y equal 3x on the interval from 0 to 3. And we'll rotate this around or about the x-axis. Okay, so we've got this line, 3x, it's a bit steeper, I guess. That should have gone through 0. It's a bit steeper than y equals x. And we're on the interval from 0 to 3. We're going to rotate this guy around the x-axis. Less, like that. Okay, and we want to find the surface area. Now, if we wanted to find the volume, we could go dx and we get nice disks, pi r squared dx. Or if we wanted to find the volume dy, we'd have nice cylindrical shells, and we could do 2 pi r h dy. But we're not trying to find the volume, just the outside edge, just the surface area. Now, if you notice, this is a fairly basic figure, right? It's just a cylinder, just a cone, excuse me. The height of the cone is 3, from 0 to 3. And then the radius, well, let's see, at 3 would be 3 times 3, so this would be 9. So the radius is 9. And the surface area of a cone, we can just get that just straight from geometry, is pi r L. Pi r L. Again, where L is the slant height. Now that L, the slant height here, that's just the square root of h squared plus r squared. So for our surface area, we can get from geometry, we've got pi. Our radius was 9. And our slant height, that's the square root of the height squared, 3 squared, plus the radius squared, so 9 squared. So it looks like 9 pi square root, that would be 9 plus 81 is 90. I I can pull a 3 out, right? Square root of 9. And that'll leave me a 10 underneath, but 10 is 5 times 2, so that can't be simplified any further, which means I'm going to get a 3 pulled out of here and a square root of 10 left. So 3 times 9 is 27 pi root 10. And this is a surface area, so that's units squared. Okay, so we got that from geometry, from just the straight formula for the surface area. And let's hang on to that. Let's write it up here. 27 pi root 10 units squared. So we know that one from geometry, just that way. And let's try to do it the calc way and see if it works. Okay, so I need 2 pi. Fine, those are just constant. Integrating, I'm going to go dx. So my frustrums are like that, right? This way vertically, so dx. Maybe I should leave a little more space. Okay, we're going to need r as a function of x. So we need that radius. And then in here, we're just filling in the ds stuff. So 1 plus, we're going to need the derivative squared. Okay. So we have 2 things to figure out. We need that derivative. We need to make sure it's defined well. It's a linear function, so we're okay. Our derivative is just constant, right? Y prime is just 3. Okay, so that's not a problem. R of x, let's see. Well, our r is being dictated by that line, that y equals 3x. So it's the y value here of that line. Cool. So that's my radius, y equals 3x. And there's our setup. The 2 pi r, oh, I forgot my bounds. We're going from 0 to 3. Nice. Well, this one we don't actually have to do a whole lot of work. That's just a constant. So we've got the square root of 10. I can pull that out. So 2 pi root 10. Actually, I can pull this 3 out as well. So let's make that a 6. So I pulled the root 10 out and the 3 out. All I have left underneath is the x. 0 to 3 x dx. So we got x squared over 2. We'll make that 3 pi root 10 x squared barred at 3 and 0. Well, the second one just zeroes out. That's just an x in there. So all I need to do is evaluate at 3. Gives me 3 pi root 10 times 3 squared is 9. And there we go, 27 pi root 10 units squared. 27 pi root 10 units squared. Beautiful. That's what worked. Okay, so in this one, the only difficulty, or the only added difference to the arc length was having to find out how are we defining that radius. But we didn't have to do much work to get out from under that root because it was just a constant and we could pull it outside. Cool. Okay, so that was just a straight cone. Let's try another one. Let's try y equal 1/3 x cubed on the interval from 0 to 3. Now again, as before, since our ds needs the derivative, we do have to be mindful that the derivative is defined on the interval. We still have that same concern, right? But here it's not a problem. Y prime is just 3 over 3 is 1, subtract 1, x squared. That's not undefined anywhere on 0 to 3, so we're okay there. So I'm trying to fill in 2 pi, integral from 0 to 3. I need r as a function of x, square root 1 plus my derivative. Well, we just found out that was x squared dx. Now let's see, this is 1/3 x cubed. It's sort of a squished, like this sort of deal. And we're on the interval from 0 to 3, rotated around the x-axis. I forgot to mention that. Around x. Okay, so something like that. And so if I'm taking my cross sections, I'm going dx. The radius is being defined again by that y equal x, or 1/3 x cubed. Okay, so it's the radius of my slice is being dictated by this curve here. 1/3 x cubed. Good. All right, so the 1/3, that's constant. We can pull that out. 2/3 pi, integral from 0 to 3. Got x cubed, square root. This is 1 plus x to the 4th dx. And at this point, I'd be in trouble, right? Well, I've got this 1 plus x to the 4th underneath that square root. I wouldn't have been able to u sub it if it weren't for that x cubed sitting outside. But if I say u is x to the 4th plus 1, or 1 plus x to the 4th, by the way, du is 4x cubed dx. The 4 doesn't bother me, right? I can always pull that outside. It's the x cubed dx that I needed. So 1/4 du is the x cubed dx here. So I needed that derivative to be there. It is there, so this is going to be a straight u sub. Just end up being a power rule. So let's pull that 1/4 out here. Well, it would be 2 over 4, so 1 over 2, so this would be a pi over 6 out here. Integral. We'll wait on the bounds because we're doing a u sub. We pulled that quarter out. The x cubed dx, that's du. We have u to the 1/2 power. So straight power rule. But now we need to change our bounds. So let's see. If x is 0, then u is 1. If x is 3, 3 to the 4th is 81, 9 times 9, so 82. Nice. And now it's just straight power rule. We have pi over 6 times u to the 3/2, 2/3, barred at 82 and 1. That would be this is pi over 9 times u to the 3/2, barred at 82 and 1. So the second one's easy, that'll just be a 1, so minus pi over 9. It's the other one that's going to be a little bit ugly. We have 82 root 82. Over 9. I suppose you could combine those. Pi, this would be 82 root 82 minus 1 over 9. Unit squared is the surface area. course, we could get a decimal approximation to that if we needed. All right, so there was the setup. Did the algebra? It wasn't too bad because we could actually do a U sub with this one. Since that radius was sitting outside, we had it. Okay, let's do one more. There's also the similar strategy, just like we did for arc length, of pulling out the least factor of x. That's another strategy that, once we get to the point where we've got something stuck underneath of that root, can try to pull some stuff out to hopefully get our U sub going. So that's another strategy that is also useful for these sorts of problems. Pull out the least factor of x, just like for arc length. They're similar sorts of problems, right? Similar formula. So let's try one more. How about y equal 2 root x on the interval from 4 to 9. And again, we'll go about x-axis. Okay, I suppose we can start just by doing a picture. 2 root x is sort of like that. And we're going to cut it off, right? It's from 4 to 9. So it's like, that's 4 and that's 9. So we're cutting that off. And then rotating it around. Like that. Okay. So our typical slice is a vertical slice, again, like that. Well, sort of. Didn't quite get it, but okay. So we're going dx, and it looks like the radius, again, is just y. It's being dictated by that curve up top there, 2 root x. Okay. Good. So let's start our setup here. We've got 2 pi integral from 4 to 9. Our radius, just dictated by the y here. It's the y of 2 root x. So there's our radius, 2 root x. Now we've got the square root of 1 plus the derivative squared dx. So I need my derivative here. Y prime is, well, 2. Let's see, that'd be a half. We've got 2x to the 1/2. So I'd multiply, that'd just be a 1. And then I need to subtract 1, x to the negative 1/2. So 1 over square root of x, x to the negative 1/2. Now I'm nervous. I've got x in the denominator. So it's possible that that derivative could be undefined. But root 4 is 2, root 9 is 3. Everything in between, we're fine. There's no 0, divide by 0 here, so we're okay. We don't have to switch and go to dy. But it's important to check to make sure, especially in this case where we've got the possibility of a divide by 0, got to double check my interval and make sure we're okay. The derivative is defined. Okay, well, we might as well leave that as x to the negative 1/2. Beautiful. There's our setup. Let's see if we can simplify some stuff. We've got 2 pi integral 4 to 9. I can pull this 2 out here, so that's a 4 pi. Got a root x, root 1 plus, well, square this up would be x to the negative 1, so 1 over x dx. And now I'm almost in trouble. I'd want to try to u sub this 1 plus 1 over x, but if I take the derivative of 1 over x, that's x to the negative 1, so it'd give me an x to the negative 2. In order to do that u sub, I need an x to the negative 2 outside, and I don't have it. But I do have a rule that says that I can combine, right? A power of a product is the product of the powers. So since I have, what I'm saying is, if I have ab to the 1/2, that's the same as a to the 1/2, b to the 1/2. So in this case, I have a to the 1/2, b to the 1/2. I'm just going to combine them. I'm going to multiply underneath. Integral 4 to 9 square root x plus, well, 1 over x is just 1. X over x is just 1. Nice. This is a straight up linear function. That means I can u sub. I don't even have to worry about, there's no constant there. It's just 1, right? U is x plus 1. So du is just dx. Only thing I really need to worry about then is the bounds. So du is dx, so I can just sub for that. Sorry, this is a pi. Don't know my bounds yet. I've got u to the 1/2 du. And let's see, if x is 4, then u is 5. If x is 9, then u is 10. There we go, it's a straight power rule. 4 pi times u to the 3/2, 2/3, barred at 10 and 5. So that's 8 pi over 3, u to the 3/2, barred at 10 and 5. So let's see, that's 10 root 10, 80 pi root 10 over 3. And 5 root 5, so 40 pi root 5 over 3. And I suppose you could combine over a common denominator and factor out common factor, but this is the exact answer. Otherwise, we're just, manipulating stuff. It can combine, but like what I was saying, we could pull a 40 pi out. Actually, we could pull a 40 pi root 5 out, but then see, we're going around in circles. So this would be what, 2 root 10 minus root 5 over 3 squared. Fine. Again, these are equivalent.